Okay, so today we are going to be talking more about acid and base reactions. Remember, this unit we're going to focus on two types of reaction, acid-base reactions and redox reactions. We're not too redox yet. We're going to talk about acid-base just a little bit more today. So first of all, let's start off with just a tiny bit of review, what an acid and what a base is. So first of all, an acid is a substance that ionizes in aqueous solutions to form hydrogen, or in other words, when you have a hydrogen compound, so you have like hydrochloric acid, which is HCl. That's going to be an acid because when it breaks apart in water, hydrogen is going to be released. So that is an acid. Okay, this will increase the hydrogen concentration in our solution. Okay, well, if we have a hydrogen ion, what do we have? What is a hydrogen ion? It is a positive charge, so it is a, more specifically, it is one lonely proton. If you take away hydrogen's electron, all that it is a proton. Because a hydrogen is one proton, one electron. So if it's a hydrogen ion, all you have is a proton. Another thing to call this is something called hydronium, which hydronium is H3O+. If you cannot see that very well. But hydronium is H3O+. H3O+. You see that a little better? Okay, it's not the same thing as hydrogen, but they're used in the same context. You can use them interchangeably. Hydrogen is just a proton. Hydronium is like water plus a hydron, plus a proton. So not exactly the same thing, but they can be used interchangeably. When you see either one of these, you know we're dealing with an acid. Okay, so there are several types of acids, which we already talked about. The first type is something called a monoprotic acid. Monoprotic acids are acids that can have just one hydrogen, so mono, one hydrogen. Okay, remember we talked about this when we learned how to name acids, right? Okay, so these are going to ionize completely. What that means is, so like for instance, if we have HCl, it means we're going to have HCl, and it is going to break apart into hydrogen and chlorine. Okay, all of it breaks apart. None of it is left. Okay, monoprotic, they completely ionize. They completely break apart into their ions. There will be no HCl left. Okay. So another type of acid is a diprotic acid. Diprotic acids, di is the prefix for two. These are acids that have two hydrogens, and they ionize in two steps. So basically, they ionize like this. They say, guess I have to. Okay, so they start off with H2SO4, and then you break off one hydrogen. So then you're left with hydrogen plus HSO4 minus. So we have an ion, right? Okay, and then what do you think is going to happen in the second step? The HSO4 minus is going to break down into hydrogen again and our sulfate ion. So they ionize in two complete steps. The next type of acid is something called a triprotic acid. Triprotic is three, so these are acids that contain three hydrogens, and they are going to break apart into three steps. What do you think those three steps are going to be? And the first step, H3PO4, is going to break off one hydrogen. You're going to have H2PO4 as a product, right? Then you're going to start with H2PO4, and it's going to break off one hydrogen. So then you're going to have HPO4 as a product. And then you have to start again, and that one will break off the last hydrogen. So in order to get phosphate all by itself, it has to break up into three steps. How many it takes to break it up? Okay, so there's a little review on acids. Let's talk about bases now. Okay, bases are substances that accept or react with hydrogen ions. So sometimes they produce hydroxide when they dissolve in water, but not always. So I don't want you guys to just get focused on looking for hydroxide, because I'm going to show you an example in a second that does not have hydroxide. So bases can do two things. They can accept or react with hydrogen, so they can gain a hydrogen, they can bond with a hydrogen, or they can create hydroxide. So you need to, when you look at bases, you need to look for both of those things. So like for instance, if we're dealing with sodium hydroxide, sodium hydroxide, if you dissolve it in water, is going to break apart into sodium ion and our hydroxide ion, right? It's producing hydroxide. Is this a base? Yes. Another example is calcium hydroxide. You dissolve that in water, you're going to get calcium plus hydroxide. Again, do we see hydroxide? Yes, so is this a base? But on the next example, we have NH3. As soon as you guys see NH3, you're going, oh, there's no hydroxide there. That looks like an acid, right? But when you mix it with water, what's going to happen is it's going to steal a hydrogen from water and it's going to become NH4. So if we look at ammonia forming ammonium, NH3 is ammonia, NH4 is ammonium. Okay, when we look at that, our initial instinct is to say acid, but if you look at what it actually does, it's gaining a hydrogen, which if you look at the definition of a base, sometimes they accept or react with a hydrogen. So this is actually a base, even though there's no hydroxide. So now you guys are asking, well, why, right? Well, let's draw the picture. Let's draw a picture of what NH3 looks like. So NH3, you draw it, we have an N, and then we have, there's nitrogen, right? And then we have 3 hydrogens. Okay, NH3 is nice and happy, right? But what do you guys notice about the way NH3 is formed? Do you guys see like a weak spot somewhere? It's going to have angles because of that, what? The lone pair, so it's probably not going to be nice, pretty straight because of this lone pair right here, which is going to make this side of the atom, what? Slightly negative, because it's going to be pushing those hydrogen bonds down. So it's going to be making that end of nitrogen slightly negative, which means it's going to be attracted to a positive charge. So therefore, a hydrogen that has no electrons is going to go, oh, look, that's slightly negative. I'm positive. Let's bond. So it bonds. And does anybody remember what the bond is called when you take a lone pair and it donates both electrons to an element for a bond? Do you remember what that's called? Coordinate covalent bond? Flashbacks coming back now. So basically, nitrogen says, I have these 2 electrons. I'm not really doing anything with them. Hydrogen doesn't have any. He's lonely. So I'm just going to be nice and I'm going to share my pair with him. And then we're short an electron, right? So then if you were to draw this, you draw brackets around it, and then you say, oh, this is positively charged, right? So NH4. This is why NH3 acts as a base when you would assume it would act as an acid, just because of its structure. Okay, so you also, when you are doing this, you need to be paying attention to stoichiometry. And what I mean by stoichiometry is, like, for instance, if we look at calcium hydroxide equation, you see how I had to balance it? So if I have 1 molecule of calcium hydroxide, I'm going to get 2 molecules of hydroxide. So you have to pay attention. You need to make sure that your equations are balanced. We just kind of need to get in the habit of making sure equations are balanced when we start to do stoichiometry with them, okay? So now let's move on to acid-base reactions. Okay, these are often called neutralization. Acid-base reaction, neutralization. What do you think I mean when I say, if you just say neutralize, what are you talking about? You want to make them kind of like, you want to find like a middle ground, right? You want to, maybe someone's really strong and somebody's really weak, so you put them together in a pair, so maybe their strength will benefit each other, right? You're trying to balance it out. So neutralization, I'm going to take a really strong acid and a really strong base, and if you mix them together, we should get somewhere in the middle. Okay, so neutralization reactions will always produce water and a salt as products. So if we take HCl plus sodium hydroxide, HCl, we see hydrogen, we're going to go, oh, HCl is going to break apart into hydrogen chlorine acid, right? You see sodium hydroxide, you see hydroxide, you're going base, correct? In your head, you just automatically go acid base. Well, when these 2 things bond, think about the double replacement reaction. So in a double replacement reaction, this, because isn't acid-base reactions, aren't they pretty much double replacement reactions? Mm-hmm. Okay, so this hydrogen is going to replace sodium. Sodium is going to replace hydrogen. Well, if we have HOH, isn't that water? Mm-hmm. Water. And then whenever we have an alkali metal forming with a halogen, it's called a salt. So we're always, in every acid-base reaction, you should get some form of water and a salt. Casey. Okay, so just in case we forgot the definition of a salt is any ionic compound whose cation comes from a base and whose anion comes from an acid. So I'm expanding that definition just a little bit more. And Casey, the handouts are up here on this chart table. Okay, the other day I had you guys write down the 8 strong acids and the 8 strong bases, right? But just in case we didn't get them, here are your strong acids and your strong bases. These guys are always going to completely disassociate in water. Always. They will always break out apart into their ions. They'll never have anything left behind. And if you notice, what do you notice about the strong acids and the strong bases? Don't they follow the most basic definition of an acid? The acids have the hydrogens, the bases have the hydroxides. They're pretty easy. So if you're ever dealing with something and you're not quite sure if it's an acid or a base, probably not one of the strong ones. And then there's one, not that one. Not the right one. Yes. No. This one's sorry. How about I come back to this side later? Okay. Alright, so let's talk about weak acids and weak bases. Strong acids and bases, they ionize completely. They make nice, pretty equations for us, right? But let's talk about weak acids. These are our weak electrolytes, which means they, conduct electricity, but not always, not completely. They're going to have like a weak charge. So if I were to hook up like a light bulb to it, it wouldn't be bright. It would be like semi-bright. Okay? So let's look at weak acids. So for instance, if I take, this is acetic acid. If I take acetic acid, and it's a weak acid. So if it's a weak acid, is it going to disassociate completely? No. So basically what's going to happen is if you see this H over here, kind of all by itself, it's not over here with the CH3, correct? What's going to happen is we're going to get CH3, COO minus, plus H plus CH3, COOH. It is not going to deionize completely. Basically, some of it will break apart, but we're still going to have some compound left down at the bottom. Yes. I'm going to draw a picture in a second. Well, I'm not adding it. There's still some left over. They don't disassociate completely, so some of it's going to break apart into ions, but you're still going to have some of it left over. That's not going to break apart, so you're still going to have some left in the compound. Yes. Mm-hmm. So, for instance, let's draw what this looks like, because I think if we draw it, we'll understand it a little bit. So, we have carbon. Okay, carbon has 4 dots, right? Well, the way it has written, whenever you guys are drawing these compounds, draw as it's written. So if you see carbon, H3, those 3 hydrogens are going to that 1 carbon. So you go hydrogen, hydrogen, hydrogen. Okay, and then next is an oxygen. Next is an oxygen, right? And then, you see how I drew it just as it's written? Just draw it straight across. So, if we look at the way it's bonded right now, let's look at electronegativity. If you guys remember, what element has the strongest electronegativity? Fluorine, followed by probably oxygen, right? Oxygen and chlorine are probably pretty high up there too. The closer you get to fluorine, the higher electronegativity. Carbon's a few steps away, correct? So carbon electronegativity is not as high as oxygen. So if we look at these bonds, hydrogen and carbon, honestly, are probably pretty similar. If I had my electronegativity values, I could tell you exactly. Okay, carbon has an electronegativity of 2.5, and hydrogen has an electronegativity of 2.1. So those are going to be pretty equally sharing, right? So if we look at the carbon to hydrogen bonds, those probably aren't going to be polar bonds, are they? They're probably going to be pretty straightforward. They're sharing relatively equally, right? Well, in the bonds between carbon and oxygen, however, carbon's 2.5, oxygen's 3.5. That one's going to be a little bit more electronegative, right? But if we compare the oxygen to hydrogen bond, oxygen's 3.5 and hydrogen's 2.1. Is that going to be a polar bond? Yes, which means that oxygen is stealing hydrogen's electron more of the time, which means that hydrogen's electron is around oxygen more than it's around hydrogen, so that makes that bond weak. So when you mix it with water, this hydrogen is going to fall off relatively quickly and become an ion and leave this negatively charged. That is why this hydrogen breaks off and not these hydrogens. These hydrogens don't have a difference in electronegativity, so they're not as weak. Whereas that hydrogen, that bond is much weaker, so that's where it's going to break apart. That's why I write it as CH3COO minus, because that bond is weak, so our oxygen will steal the electron, hydrogen will be left deficient, go into solution. Yes? What other two? Oh, I just forgot to draw it. He's right here. I forgot to draw him. Sorry. Got in the pattern. Just forgot to draw C. But everything else would be still the same. Okay. So let's look at another example. Let's see if we can do another example. This one is HF. HF is also a weak acid, which means it's going to break apart. When it breaks apart, it's going to ionize, yes, but is it going to ionize completely? No. So what do you think our products are going to look like? H plus. Okay, what this means is, yes, it is going to balance. Yes, it is going to dissolve in water, but not completely. So this is going to be a weak electrolyte. Yes, it's going to conduct electricity, but not as well as it could. Okay, let's do another example. We have H2CO3, which, if you remember, what do you think the name of this guy is? I'm going to review naming of acids in just a second, but what do you think the name of H2CO3 is? Carbonic acid, which sounds a lot like something we have in soda. Carbonation. So H2CO3 is actually what is in your soda. Carbonic acid is added to soda to give it that fizziness. Okay, because as carbonic acid breaks up, we are going to get H2O and CO2. Fizzies. That's why your soda fizzes, because it has carbonic acid in it. When you mix it with water, which soda is made with water, right? That's why fountain soda is better than bottled soda, because the carbonation is added right then. The syrup and the carbonation are kept separate until you're ready to drink it. That's why it's much more foamier, that's why it's much more bubbly. That's why some people like the taste of it better, because it's freshly, the reaction's happening right then. In a bottle or in a can, it's already been added, and so it's been sitting there, so the reaction's already taken place. The longer it sits there, the less the reaction's going to happen. That's why soda goes flat. You guys learn something every day. Okay, so let's look and let's see what weak bases do. Weak bases, same basic concept. They're going to ionize, but not completely. So what do you guys think is going to happen with beryllium hydroxide? What are our products going to be? Beryllium 2 plus hydroxide minus plus beryllium hydroxide 2. Correct? Yes, some of it's going to break apart, but not all of it. You guys see how I'm balancing it as I go? Yes. The hydroxide too? Oh, like why is beryllium hydroxide still left over? Because it's not ionizing completely. So we're talking about dissolving these in water. So if I take beryllium hydroxide and I put it in water, it's not all going to dissolve. It's not all going to break apart. Some of it's going to left behind. That's why we're putting it in our product line too. Because weak bases do not dissolve all the way, so they're still going to exist. It's not going to break apart into beryllium hydroxide completely. We're still going to have some of our reactant left over. That's why I'm putting it over there. Okay, the next one, magnesium hydroxide. Is that going to look pretty much the same?
Yep.
Yep. Well, let's not draw that one out. Let's look at NH3. Let's try to do this one again. Okay, so we know NH3 is a weak base, even though when we look at it, we think acid, right? But it's not an acid because we drew out the structure and we know it has that lone pair, right? So NH3, if you add it to water, you know that water is going to contain some hydrogens, correct? So what is our result going to be? NH4 plus, we're still going to have some NH3 in there. Because it does not dissociate completely, it's not going to bond with all our hydrogens. So we're probably still going to have some ammonia left over. Ammonia actually, ammonia. You guys know that's a cleaning product, right? It actually, the longer you leave it sitting, like you buy it and say you have it under your cabinet for years, after a while it just turns into water and it won't be ammonia anymore. It all reacts because it's sitting there and it's constantly going back and forth, and eventually there won't be anything left. It takes a long time, but theoretically, after a while, you should just have water.
So we only have to add the hydrogen in the reactant side
With bases that, there's other examples of bases. I can't think of one off the top of my head, but there's other bases that also add hydrogens. And the hydrogens are there in the other ones. They're like understood to be there because we're putting these in water, but in order to get our reaction to work with ammonia, we have to put them there. But it's not that they're not there in the other ones. It just, we don't have to, they don't react like they do with ammonia. Okay, so naming bases is really easy. It keeps its name. So beryllium hydroxide, done. Magnesium hydroxide, done. There's no set of rules for naming bases. Naming bases is really easy, except for ammonia. Ammonia doesn't have a hydroxide, so it's good anyway. Naming acids, we should remember this. Does anyone remember how to name an acid? How do we name a monatomic acid? Hydro, right? Hydrocarbonic acid or right? You add hydro, you add acid. Okay. What about 8? Okay, you change the ending to ic, so this would be like carbonic, and then you add acid. Carbonate, if you're doing with the polyatomic ion, carbonate, you change the 8 to ic, so you have carbonic acid. Okay, and then if you have a polyite form, you change the ite to us. So if we are dealing with chlorite, it would be chlorous acid. It's usually hypochlorite, so it would be hypochlorous acid. That's what I have to say. Okay, just to review our naming of acids. Okay, this is where we get to the new information. Okay, as we were just discussing, do all acids fit nice and pretty under the acid definition? Do all bases fit nice and pretty under the base definition? No. So there are actually 3 acid-base theories. Okay, and not every acid will fit into each theory. It's basically you have to look at what acid or base you're looking at. So first of all, acids and bases have been described for over 300 years. However, scientists don't always agree on the definitions because science is not a nice pretty box where everything fits in and you can shut the lid. That's just not how things work. So we have to create different rules and different laws for different things. Okay? So the first type of acid base is something called an Arrhenius acid base. Okay, I want everyone to practice saying that. How do you say it? Arrhenius. When you read it, you go, but it's Arrhenius. Arrhenius. Okay? Then we have Bronsted-Lowry acids and bases, and lastly we have Lewis acids and bases. Lewis, that sounds familiar. What does that sound like? Lewis dot structure. So this base is probably going to have something to do with electrons. He did the Lewis dot structure, which is valence electrons. This theory involves electrons. So let's talk about Arrhenius acids and bases. Okay, Arrhenius acids and bases, this was proposed in 1887. This was one of the first theories. Okay, he said that acids are hydrogen-containing compounds, and when you put them in water, they are going to yield hydrogen. Always. In order to be an acid under this theory, you have to contain hydrogen, and you have to produce hydrogen ion. Okay. He then said bases have to contain hydroxide, and they have to produce a hydroxide ion when mixed with water. So right off the bat, does ammonia fit into this definition? No. Okay. Arrhenius bases are stronger when you combine them with an alkali metal. So if you look back at our list of strong bases or strong acids, weren't they mainly with alkali metals? Mm-hmm. Okay, so these guys are usually stronger when they are combined with alkali metals. Okay, so let's look at an example of this guy. So, for example, carbon has a lower electronegativity than oxygen, so the hydrogen attached to the oxygen will break off because this is a monoprotic acid. I just drew this nice pretty picture for you guys and explain why hydrogen breaks off, correct? Okay, so, do you want me to draw a picture again? No? Does everyone understand that one I just drew? Okay, so now the next theory deals with Bronsted-Lowry acids and bases. This was developed by Bronsted and Lowry in 1923. Two scientists worked together to do this. What they said is, okay, the Arrhenius theory works most of the time, but not always. Okay, so instead of just saying hydrogen, they're going to make it a little bit more broad. Instead of saying hydrogen, they're going to say acids donate hydrogen ions. Bases accept hydrogen ions. So basically this one threw out hydroxide, right? So ammonia is going to work under this theory, right? Because they accepted an ion. So that means they were a base under this theory because they accepted the hydrogen. So for example, we have hydrochloric acid. Okay, so hydrochloric acid, we mix it with water, which is what we do when we're making an acid. We're going to get our hydronium ion, and we are going to get chlorine. Now, when you look at this theory, under the Bronsted-Lowry theory, there's this whole concept of something called a conjugate acid and a conjugate base. Okay, so if you look at it, HCl is an acid. Okay, well, what happened to the hydrogen of the HCl? Where did it go? The hydrogen of the hydrochloric acid bonded with the water to form hydronium, so therefore hydronium is the conjugate acid. They go together. The hydrogen left hydrochloric acid and it went to hydronium, so that's why we call it the conjugate acid. That's where the hydrogen went. And if you look at water is acting as the base, right? So the conjugate base is where the hydrogen left from. Conjugate acid is where the hydrogen is going. Conjugate base is where the hydrogen came from. So those two things go together. So HCl and Cl minus are a pair. H2O and H3O plus are a pair. They're the conjugate acid, conjugate base pairs. So this kind of, basically you just have to look at where the hydrogen is going, and you can kind of piece together what the pairs are. Okay, and we're going to do lots of examples here. So we should be good on this front. So if we look at ammonia, NH3 plus H2O, we're going to get NH4 plus hydroxide. So technically, if we write it like this, it kind of almost fits in both theories, doesn't it? Okay, so Bronsted-Lowry acids have conjugate bases, conjugate acids. So if we break this down, we know NH3 is going to act as a base. We know in this scenario, H2O is going to be acting as the acid, whereas in the last one, it was acting as the base, right? And we're going to talk about why water does that in just a second. But NH3 is going to be gaining a hydrogen, which makes NH4 its conjugate acid. So our acid-base pair is going to be NH3 to NH4. They gained that. So the base and the conjugate acid, they go together. Okay? Then on H2O, It lost its hydrogen, so then these two are going to be the pairs. These two are going to be pairs. Okay, we have an acid-base pair. Conjugate acid, conjugate bases. Okay, like I just said, water's a special case, and we're actually going to skip the Lewis acid section for just a second, and we'll come back to it after the next time. But amphoteric substances. Water, amphoteric substances are substances that can sometimes accept hydrogen, sometimes they donate hydrogen, sometimes they form hydronium, sometimes they form hydroxide. Water is a perfect example of one of these substances. The reason it is referred to as amphoteric is because it can be either or. It will never be both at the same time, but under different circumstances, sometimes it acts as an acid, sometimes it acts as a base. Which, if you guys think about it, water, pure water, not tap water, has a pH of what? Does anyone know? 7. 7 is smack dab in the middle of our 0 to 14 pH scale, right? So is water an acid or a base? It's neither. It's neutral. So therefore, because it's neutral, if you mix it with an acid, it's probably going to act as a base. If you mix it with a base, it's probably going to act as an acid because it's trying to neutralize it, right? So it's trying to come to a middle somewhere in that. So that's what amphoteric means. Other amphoteric substances may include metal or metalloid oxides, amino acids, which are in your body, proteins, and ammonia. So this is a lot of times, these reactions take place a lot in your body system. That's why you can eat acidic and basic foods in your food. Okay, yes. I don't know. Yours are different. Yours is different than mine, so I don't know what's the same thing. An acid or a base. Okay, so let's talk about that third theory now. Okay, the third theory is Lewis acids and bases. We know that this is proposed by Gilbert Lewis in 1923, so this came around the same time as the Bronsted-Lowry theory. I think it was even the same year. We already know Lewis came up with the Lewis dot structure, so he was studying electrons. So it makes sense that this theory is going to involve electrons. He said that acids deal with the donation or acceptance of a pair of electrons. So he's almost even making this a little bit more broad. He says that acids accept a pair of electrons, where bases donate a pair of electrons. Acids accept a pair of electrons, bases donate a pair of electrons. So for instance, if we look at just the reaction of water, hydrogen, the hydrogen ion, H+, we know is electron deficient, right? This one has no electrons, right? Hydroxide, we know, has an extra electron, right? Okay, so if we look, let's actually draw this out. So hydrogen is sad. He has no electrons, right? Oxygen looks like this. So oxygen goes 1, 2, 3, 4, 5, 6. We know he's bonded to hydrogen, right? And we know he has an extra electron. So hydroxide looks like this. Hydrogen looks like this. Hydroxide is going to feel sorry for hydrogen, right? Hydrogen's positively charged. He has no electrons. He has nothing. So, anyhow, hydroxide has lots of electron pairs, right? He has 3 electron pairs, doesn't he? So, if we look at this, hydrogen's sad, he has no electrons. Oxygen has plenty to share. So what he's going to do is he is going to feel sorry for hydroxide, and he's going to go, okay, I'll share this, maybe I'll give this to you. I'll share this with you so that everybody's happy. And he is going to make, what is this bond called again? Coordinate covalent bond to get H2O. So if we look at the definition of this, who is donating the electron pair? Hydroxide. So that makes hydroxide a base. Hydrogen is doing what? Accepting the electron pair, so that makes him an acid. Base acid. Who's base? All right, I'm going to go ahead and let you guys take a break now. I think the bell's going to ring in just a minute anyway. Be back by 9. I'm going to give you guys a 10-minute break. Okay? All right, I want to show you guys another example of the Lewis acid bases because there's another example of BF3. Okay, boron was one of those exceptions to the octet rule, right? There were several exceptions to the octet rule. Boron's one of them because they only have 3 valence electrons, so they're the exception. So if we draw BF3 out, we're going to draw boron. He has 3. He's going to bond to fluorine. He's going to bond to fluorine. And he's going to bond to fluorine, which makes boron electron deficient, right? Is he following the octet rule? No, but he's pretty happy because he doesn't have any unbonded electrons. But that leaves a huge hole right here, correct? So basically what's going to happen is if we put this in water, what do you think is going to happen right here? So what is he going to gain? We're talking about Lewis acid bases. What do you think he's going to gain right here? An electron. So BF3 is going to act as, or is he going to act as the base or the acid? The acid. He's going to act as the acid because he's going to try to accept electron pairs. So I wanted to show you one more example of that. Okay? All right, so let's continue on. Let's start talking about titrations now. Okay, a titration is a lab technique used to determine the concentration of a particular solute in a solution. So basically what it means is if I'm given a solution and I don't know what its pH is, I don't know what the concentration of hydrogen ions are, I don't know what the concentration of hydroxide ions are, and I'm trying to figure it out, we use a method called a titration. In order to do this, we have to have something called a standard solution. This is a solution or reagent of known concentration. So for instance, if I went in there and got a stock solution that I ordered from the chemical company and it says it is 6 molar, I can pretty much trust that's probably going to be 6 moles per liter of solution. It's a known concentration. Okay? So I could use how that guy reacts in a titration to compare it to maybe my unknown to see if maybe it has a similar molarity. Okay, titrations are used when we are using acid-base reactions. So, for a titration to work effectively, we have to have stoichiometrically equivalent quantities of the reactants must be brought together to reach the equivalence points. Isn't that a fun sentence? Everyone, try it once, just kidding. But basically what that means is we don't have to be equal. It doesn't mean that you have to have equal reactants and products. It means that they have to be equivalent, which means how to say this. Let's just go on and see if it'll kind of click in a second. Doesn't that, you don't always have to be, have you guys ever heard the saying equal is not always fair? Okay, that kind of applies here. When we say we want them to be equivalent, does not mean that they have to actually be equal. It means that we want hydrogen and hydroxide coming in and out of solution at the same speed, not exactly equal amounts. Okay, so this is called the equivalence point. Indicators are used to determine when the equivalence point has been reached. So when we have reached this neutralization median point, when hydroxide and hydrogen are coming in and out of solution at the same time, we call this the end point. This is when we often see a color change. Okay, so if I mix water with an acid with water, and I sit there, do you think anything? Are we ever going to notice when it reaches this equivalence point? No, because most acids are clear. So what we do is we actually add something called an indicator into the solution. An indicator, there are several different kinds. For instance, these are just kind of some of the main ones. Phenolphthalein, which is right here, is the most common one used because if you notice where it falls on the pH scale is it's not exactly neutral, right? It doesn't fall in the range of 7. It falls in the range of 8, right? It'll start to change color at 8, which is not exactly a pH of 7, but the reason that indicator is used so often is because it's an obvious change. When you see the faintest pink, if you take a clear solution and you turn it pink, it's going to be very, very obvious, right? Okay, so even though when it starts to change, you're technically at a pH of 8, it's still the most commonly used because it's easiest seen. We could use the next one up that goes from yellow to blue, but the bad part about that is if you notice in the middle, it turns green first, right? It's not as easy to see a change from greenish blue to blue. That's not as obvious of a change as going from clear to pink, right? So that's why that indicator, even though it does more what it's supposed to do, we don't use it as often because it's not as obvious of a change. And not all reactions are going to be neutralization reactions. So if we're doing some of the other reactions like the redox reactions or the precipitation reactions that I was just talking about, sometimes we'll use different indicators because maybe we don't want to know when they reach a pH of 7. Maybe we want to know when it reaches a pH of 4. So we might use methyl orange because then when it goes from red to yellow, which is probably going to be pretty obvious, we know that it has reached a pH of 4. So we can use all these different indicators because clear solutions are hard. If you hard to see a change, so if you put a little bit of a color in there, when it reaches this pH, it changes colors. Ooh, we can see that, so we know when to stop. So now we have our solution at an exact pH. Yes.
What exactly is
pH is hydrogen hydroxide concentration. So at 7, your hydrogen and your hydroxide concentrations are equal. At pH of 14, your hydroxide concentration is really high and your hydrogen concentration is really low. At a pH of 3, your hydroxide is really, really, really low, and your hydrogen is really, really, really high. So this is when we're dealing with acids and bases. It's never all hydroxide, never any hydrogen, and it's never all hydrogen, no hydroxide, because water is always going to have both forms. But if you are a strong acid, you're going to have more hydrogen than hydroxide, and it's just like a scale. It just kind of switches places. But in the middle, it should be equal. Does that make sense? All right, so let's see if we can do some acid-base reactions. So example problem number 1 says, what is the molarity of sodium hydroxide solution if 48 milliliters is needed to neutralize 35 milliliters of our 0.144 molar sulfuric acid solution? Nope, thank you though. So, when we're doing this, you have to figure out again what goes together, right? So we know that we're going to neutralize the solution, right? And we want to neutralize it to 48 milliliters, right? So that kind of helps me know where to start. When I'm starting these problems, and just like so far this year, there's more than one way. But the way I start these problems is I start with the items that go together. So I'm going to start with 35 milliliters because it goes with the 0.144 molar. I'm going to start with these two information. So I'm going to write down 35 milliliters, and I'm going to do stoichiometry. Okay, then I have to use my molarity. So what's going to go on top, what's going to go on bottom? I'm going to put moles over liter. 1 liter, 0.144 moles. Uh-oh, problem, what do we see? Right, so I'm going to go 1, 2, 3, add a 0, cancel out my milli, right? So now we're in the same unit, correct? Now what do you think we should do? We're in moles now, but we know what moles we want. Molarity, but we have to kind of do another step here because we're not wanting moles of sulfuric acid. We are wanting moles of sodium hydroxide. So we're changing compounds, correct? So we're going to be doing actual stoichiometry. So remember, this is H2SO4. How do we change compounds? What step do we have to do? Mole to mole. So Now we have to look at our balanced equation, so it's already balanced for us. So if we look at sulfuric acid, there is 1 mole of sulfuric acid for every 2 moles of sodium hydroxide, correct? So now we have changed our compound, correct? Okay, so this cancels, and we are left with moles of sodium hydroxide. But we don't want moles of sodium hydroxide. We want molarity. So we have to take our moles and we have to divide it by, so nothing goes on the top. This time it's going to be 48 milliliters. But we don't want milliliters, we want liters. So we have to go 1, 2, 3, add a 0. And then all we have left to do is the math. So we're going to take 0.035 times by 0.144, divide by 1, times by 2, divide by 1, and then we have to divide by 0.048, and we get an answer of 0.224 molar NaOH. So stoichiometry, yes. Molarity problem, yes. So we're basically doing molarity and stoichiometry at the same time. Right? Not bad, because we should be pros at doing stoichiometry right now, right? Okay, so, but because I like to do more than one example, let's do another one, okay? Example number 2, it says, the quantity of chlorine in a water supply is determined by titrating the sample with silver. How many grams of chlorine are in a sample of water if 20.2 milliliters of a 0.1 molar silver is needed to react with all chloride in the sample? I don't know about you guys, but when I read word problems, I go, right? So I'm trying to teach you good skills by having you circle and underline, right? So first of all, I'm going to circle the things that go together. These things go together, right? And we are wanting grams. The last problem was asking us for molarity. This problem's asking us for grams. So same basic concept, different steps, right? I circled what we're starting with. I squared what I'm going to end with, right? So I always start with the volume. You could start with the molarity. It really doesn't matter. It's easier for me to start with the volume. So I'm going to go 20.2 milliliters. Okay. Our molarity, I'm going to put 0.1 moles of silver over 1 liter of silver. Uh-oh. What's wrong? We have milliliters and liters. We can't do that, so we go 2, 3, add a 0. Milli's gone. Right? Okay, but we don't want moles of silver. We want grams of chlorine. We can't go from moles of silver to grams of chlorine. We have to do a mole to mole now. So, oh, looky there. Our equation is nice and pretty and balanced for us. Don't we like that? So we have 1 mole of silver, 1 mole of chlorine. But we don't want moles of chlorine. We want grams of chlorine. So look at the periodic table. There are 35.45 grams in 1 mole. So if you do 0.02 times 0.1 times 1 times 35.45, you should get 0.0716 grams of chlorine. So, not hard, just kind of, you have to make sure you understand what the problem is asking you for and what the problem is giving you, right? If you can't figure that out, you're going to struggle with this part, correct? Yeah. All right, so I have given you another handout, right? One of the handouts is dealing with the Bronsted-Lowry. Well, actually, both of them are dealing with the Bronsted-Lowry acids, bases, conjugate acids, and bases. We're going to work on that today. And then tomorrow, I'm going to give you guys some more examples, or you're going to do some problems like this. I don't have